Today we are going to start section 1.7 and we are going to write and evaluate exponential expressions to model growth and decay situations. Now, when we're all done with the lesson for today, you'll be able to graph a function, the function like the one that I have right here. Let's start out today with a little bit of a warm-up. What I'd like you to do is pull out your calculator, whether it be your phone or your graphing calculator or just a simple little calculator that you have, but it must have a button on it that looks something like y to the x, or sometimes it looks like x to the y. So pretty much any scientific calculator is going to work. Now what I want you to do is we're going to enter these four equations into your calculator, and I'll pause it here in a moment. But what I want you to do is, when you enter these in, enter this part of it in first. And then after you enter that part of it in, then you're going to times it by the 100. Okay, go ahead and pause it at this moment. Okay, now that you've worked through these, let's go ahead and see how you did on finding these answers. So 1 through 4, you should have gotten those answers. Here are the vocabulary that we're going to be learning about this section. So go ahead and you can write this down, or you can kind of pause it if you want and get those and space them out a little bit in your notes, or what you could do is just wait till we talk about it within the notes. Either way, it's up to you. In this slide, we're going to take a look at Moore's Law. Now, Moore's Law is an example of where exponential growth occurs in today's world. Now, real quickly, let me just read what this statement says. Moore's Law, a rule used in the computer industry, states that the number of transistors per integrated circuit, in other words, the processing power, doubles every year. So beginning in the early days of the integrated circuit, the growth in capacity may be approximated by this table that's right down here. Okay, so now what this is meaning is, let's say that some of you have an iPhone. And in having an iPhone, let's say that you had an iPhone and you had the 3. And then there was the 3S. And then you had the 4. And then you had the 4S. And then you had the 5. And that's where we currently are. Well, each year one of those phones came out. And when each one came out and there was a year between it, that meant that the processing power of the next iPhone would be twice that of the processor of the previous phone. Now, I'm talking mainly phones here, but it also works in the real computer world as well. Okay, so for example, if you take a look in 1965, you had 60 transistors. Now, notice in 66, it doubled to 120. And so on and so forth, and you can see just what's happened up to 1971. Alright, so that is an example of where you see exponential growth. Notice it started at 60 and it grew just over a matter of about 6 years into 3840. Now in this slide we're going to define an exponential function. So an exponential function, so in your Cornell notes on the left hand side, if you would write the word exponential function. And then on the right hand side, an exponential function is the function f of x equals b to the x, where b is your base and x is going to be your unknown, your independent variable, which means f of x is going to be your dependent variable. Now, your b value is going to be a constant. So an example of this may look something like this. Let's say I were to write f of x is equal to 2 to the x. Now, up to this point, we have never had a variable up here. Now we're going to have a variable in the exponent. Okay, so let's uncover a few of these little things here that we have. First of all, the b, we indicated that the b was the base. Then we said the x was the exponent. And the restriction there where b was going to be greater than 0, and of course b cannot equal a 1. Now you may be saying, why can't b equal to a 1? Well, we're going to get into this at another point, but real plainly, if b is equal to a 1, you have 1 to the x, which means you just have a horizontal line. Okay, let's begin today with graphing the function that I just gave you. Now, a moment ago I gave you this function, f of x equals 2 to the x. Now, we're going to graph that function. Now, something that I need to recognize here is if we're going to graph this function, I need to select some domain values, and then I'll get some resulting range values out of it. Now, what domain values are we going to use? Well, I would say the domain values we should use are ones that are going to give us back a dependent value that is going to be real. Is there anything in the set of domains that will not give us a real number back? The answer to that is no. Everything's going to give us a real number back. So we can choose whatever domain value we want. So the domain is going to be the set of real numbers. Now, I have chosen a few values here, so we're going to choose these. Now, in choosing these, I want you to plug each one of these back up into here, and we're going to get a range value from it. So using your calculator, just take 2 raised to the, 2 raised to the negative x, and then tell me what you get, and then write it down. Okay, pause the video at this moment, and I want you to generate those values. Now that you've generated these values, this is what you should have come up with right here. Alright, now, let's take a second and I want you to draw a graph, an xy coordinate plane, and plot each one of these ordered pairs. For example, you're going to plot negative 2 1/4, and then you're going to plot negative 1 1/2, and so on and so forth on your graph, and then I want you to draw a line. Okay, go ahead and pause it while you're doing that. Okay, now that you've done that, let's go ahead and compare what you have with what I have. So, let's uncover this here a little bit. There you go, and there's what your graph should have looked like. Now, let me show you how to do it with your graphing calculator. Take your device, or you can take the link on our math website and use the graphing calculator there. Enter the 2 to the x. Now, when you enter it in, you're probably going to want to enter it in something like this. It's going to be f of x equals 2, and then hit the caret button, and then type in the x. That throws that x into the exponent part. Okay, so go ahead and pause it and work through it with your calculator. Okay, now that you've done that, does your graph look like the one that you graphed by hand? Okay, fabulous. Okay, let's go on to the next slide. If we observe the graph that you just did, you're going to see something. You're going to see the graph comes down and it's going to become extremely close to the x-axis, but you know what? It doesn't actually touch it. Now, this last section that we covered in class, we learned a little bit about something called an asymptote. The asymptote, the graph approaches and becomes closer and closer and closer to that asymptote, but it doesn't touch it in most cases. Okay? So, in your Cornell notes, you have asymptote. Go ahead and write that down. And an asymptote is a line that a graphed function approaches as the value of x gets very large or very small. Okay, so that's your definition of an asymptote. The asymptote for this function is what? Can you see what it is? Well, yeah, probably you can. If I kind of put it right in here, it looks like it's going to be the x-axis. Now, we're going to see some characteristics regarding an exponential function here. If you look at f of x equals a times b to the x. Now, first of all, if a is always greater than 0 and b is going to be greater than 1, then that type of function is a function called exponential growth. So, on the left side of your Cornell notes, write down exponential growth, and on the right side, you're going to write a function of the form f of x equals a times b to the x with a greater than 0 and b greater than 1. Now this type of function is said to be an increasing function. In other words, as x becomes large, you're going to see y becomes large. That means the function increases. Now, what happens if your b value here, if your b value right there, is between 0 and 1? Okay, well, if it's between 0 and 1, for example, let me give you an example. Let's say that I give you f of x is equal to a, and it could be any a value. So let's go ahead and just give it a value. I'm going to just say it's 1. Okay, and I'm not going to put it there. But my b value is, say, 0.5 raised to the x power. Well, that function, because this b value is between 0 and 1, it is going to be a decreasing function. It is called exponential decay. This means that the function decreases as x increases. All right, now let me give you a little picture of what that's talking about. Okay, here's an increasing function. I'm going to take a coordinate plane, and this is an example of an increasing function. Now let me give you an example of a decreasing function. Give you a coordinate plane here, and this is an example of a decreasing function. Notice here, as x becomes larger, y becomes larger. Here, as x becomes larger, y becomes smaller because it approaches the x-axis. Now in this slide there's just a couple things that we want to remember. So I'm going to just kind of read through this here quickly. In the function y equals b to the x, y is a function of x because the value of y does what? Well, it depends on the value of x. Alright, it depends. In other words, you plug a value in for x and you get a y value back. Alright, now for a negative exponent, remember what the negative exponent did. Remember, we had a word for that. It reciprocated it. In other words, if you add x to the negative 2, you put 1 over it, so it's 1 over x squared. Okay, so keep that in mind. Now we're going to work through some examples, and in these first examples there's a few steps we're going to do. First of all, we're going to determine if it is a increasing or decreasing function. In other words, does it show growth or does it show decay? And then we're going to graph it. So first of all, let's go ahead and take a look at this here. Look right there, 1.05. Now what we have to remember, is it greater, is that b value greater than 1, or is that b value between 0 and 1? Because remember, if the b value is between 0 and 1, it's going to be a decreasing function. In other words, it's exponential decay. If the b value is greater than 1, then it's going to be exponential growth, like that. So, first of all, let's identify what the b value is. The b value here, well, go ahead and take a look at it. What's it going to be? Yep, 1.05. Now, since the base is 1.05, that means it's going to be what? Growth or decay? Well, if you said growth, I agree with you. Why? Because it is greater than 1. Alright, now let's move on to the second step. In the second step, what I want you to do is use the website, the graphing calculator website, or your device, and I just want you to graph that function, and then we're going to compare it with the one on this page. Go ahead and pause it and graph that function, please. Okay, now that you've had it to graph, let's go ahead and see if we agreed with you. Okay, that's the way it should work. For this next problem, I want you to try it. So go ahead and pause the video and you work through it, identify what the b value is, be able to tell me whether it's the function is going to be increasing or decreasing, and then go ahead and graph it using either your device or the graphing calculator website. Now that you've done that, let's take a look at what you've come up with here. You should have identified that the b value is going to be 1.2. Because it is greater than 1, that means it's going to be you said it, exponential growth function. Very good. All right, now let's go look at the graph. In looking at the graph, there's a table here, so you could actually plug some values into that function. You know, honestly, if it were me though, I probably wouldn't do the math there. I would just use the graphing calculator feature that shows the table, and I would just write the values down from the table. So, -12, what did you come up with? Okay, go ahead and pause it and write those values in for the table, please. Okay, now that you have it, for -12, what did you get? Well, I have 0.65. -8, what did you get? Well, I got 1.2. All right, let me just uncover the rest of these, and this is what you should have gotten for each of those domain values. And then the graph of it should look like this. Now, in your Cornell notes, be sure to write down not only the table, but also the graph. Now, notice how the graph is labeled. Make sure you label this graph just as it shows here. And in your notes, I'd like you to go a step further, please. I want you to make sure you do the asymptote. So go ahead and label the asymptote running right there like this, and then label it. And remember, it's going to be the x-axis, or y equals 0. All right, now let's go ahead and take a look at where we can apply some of this. Now, you can model growth and decay by a constant percent increase or a constant percent decrease with the following formula. Okay, so here's the formula that we're going to use. Now, I'm going to go ahead and write down this formula, please, in your notes, and we're going to label the individual parts for it. So, the A value is the initial amount. It's the amount that you started with. If we're talking, you started with 5 marbles and you're going to add marbles exponentially for t time period, then 5 is what you put for the A value. That's going to be your starting. If we're talking money, that's how much you invested initially. Now, the T value. The T value is the number of time periods. For example, are we talking, for example, years? Or are we talking days? Or are we talking months? So, you determine, the number of time periods is what T is. Now, your R is the rate of increase. Okay? The rate of increase. And, of course, your A of T is your final amount. It's the amount that initial amount is going to grow, or in some cases, decay, or over a time period. Now, something in this next paragraph down here I want you to know. It says, in the formula, the base of the exponential expression 1 plus r is known as the growth factor. And of course, 1 minus r is known as, you said it, the decay factor. All right, go ahead and pause the video and make sure you have this very important formula down. On this slide is just a real quick little hint here. And when you're entering these into your graphing calculator, I know you probably already know this, but I just want to give you a little bit of instruction of how you enter this into your calculator. When you enter it into your calculator, you're going to have y1 equals, you put in your initial values, 5,000, then make sure you hit a times. That's a times right there. So make sure you go times and then type in your b value, 1.0625. Which means, because that 1.0625 is greater than 1, what is it going to be? Increasing or decreasing? If you said increasing, I agree with you. And then put the caret and then the x. Now, what if your formula says t? For example, the formula that we just used said t. How does that happen? How do I do that? Well, if it says t, we can't put t into the graphing calculator. So instead of t, we just plug in an x. Let's go ahead and work through a couple examples here. It says in this first example, Clara invests $5,000 in an account that pays 6.25% interest per year. After how many years will her investment be worth $10,000? Okay, so what do we know first of all? What is the $5,000? Well, that is her initial amount that she put in there. That is the A value. Okay, The 6.25, that is the interest rate. Okay, so you're going to take that 6.25 and you're going to change it to a decimal, so 0.0625. Now, after how many years will it grow to $10,000? In other words, we want a final amount to be $10,000. So, we're going to plug this into the formula, and it's going to look like this. Okay, so we're going to plug 5,000 in for the A. We're going to plug in 0.0625 in for the R. And then we're going to add the 1 and the 0.0625 together, and it's going to look like this. One point of clarification that I just want to make sure you don't do. Do not multiply the 5,000 and the 1.0625. Notice that the 1.0625 is raised to the t power. So don't multiply the 5,000 and the 1.0625. Leave them separate. Matter of fact, you see how I've indicated here, I'm put parentheses around this? Put parentheses around there. Okay, for step number 2 and number 3, we're going to use the graph and we're going to use our trace feature of our calculator to calculate about how many years. Now notice I said about how many years it's going to take in order for the investment to increase to $10,000. Now to do this, we're going to kind of approximate the domain. In other words, just guess. So I would set a max of, an X max of, say, somewhere around 20 or 30. And I would set a Y max to be something over 10,000. So maybe you could go, I don't know, 12,000 for example. All right, now when you graph it, the graph should look like this here. This is what mine looks like. All right, now you're going to notice as you do this, you're going to notice the function goes up, and as you trace it, it's going to go up there. Now you want to keep going until you see a Y value right here of about 10,000. When you see a Y value of 10,000, then you can stop and you can see what year you are on. So you could see that you reached about $10,000 after 12 years. Now there's another way you could do this, and the other way you could do it is by viewing the table. If you viewed the table, you could see that at 12 years, right here, you were at 10,349. All right, now you could actually zoom in a little bit closer and try to get a little bit more closer, on that as well. It turns out the answer that it's going to come out to be that it reaches $10,000 at 11.43 years. Okay, let's go do another example, and I'm going to let you try one this time. All right, this problem says that in 1981, the Australian humpback whale population was 350. Okay, so I'm going to circle that. That means my A value, that's our initial amount, 350. And it's going to increase at a rate of 14%. So that means our R value is going to be 0.14. It says write a model population growth. Use the graph to predict when the population reaches 20,000. Okay, so we want to know when the population equals 20,000. So when we graph it, we're looking for an independent value that is going to be matched with the dependent value of 20,000. Okay, so go ahead and pause it, plug that in, and simplify what you can, and then go ahead and graph it and see if you can predict after how much time will the population reach 20,000. All right, now that you've done this one, this is what it should have looked like. You should have plugged 350 in the 0.14, and then you can simplify that a little bit. So you're going to get 350 times 1.14. Noticing here, this B value here is greater than 1, so you know it's going to be increasing. Now, you graphed it, and using your device or your graphing calculator or your computer program, you can trace it and kind of see just where it's going to be, where it's going to reach a population of 20,000. Okay, so my graph looked like this. So I want to go up to where the population, when it's going to reach 20,000, and notice it reaches 20,000, about 20,000, after 31 years. So the way we're going to say that, it will take about 31 years for the population to reach 20,000. Okay, let's take a look at another situation. It says a city population which was initially 15,500 has been dropping. Okay, dropping means it's going to be what? Population increase, population decrease? Yes, it's going to be a decrease situation. In other words, we're looking at decay. Okay, so looking at this problem, it says been dropping at 3%. Okay, so let's do that. Okay, now it says write an exponential function and graph the function. Okay, so use the graph to predict when the population will drop below 8,000. Okay, so first of all, what is my A value? Well, it's right there. So A you know to be 15,500. Okay, what is our R value? Well, our R value is going to be equal to 0.03. It told us it was dropping. That's why notice when its population increase, I use 1 plus R, but when its population decrease, you use 1 minus R. Okay, so let's hold the phone just for a second. Stop everything. Make a little star off to the left side in your Cornell notes. And what I want you to write there is I want you to write what I just stated. Population increase, you're going to use 1 plus R. So in your notes, go population increase, you're going to use 1 plus R. Or instead of increase, if you want to use population growth. Then if you say population decrease, or you could say population decay, you're going to use 1 minus R. So make yourself a note that indicates that. Alright, so now I want you to pause it, plug the values into the formula, then I want you to graph it and see if you can trace it to predict when it's going to be below 8,000. Okay, now that you've done it, let's go ahead and look to see if what I have, you have. So you plug the 15,500 in there and the 0.03, and you simplified that. So you simplified it by just adding what's inside the parentheses right here. So 1 minus 0.03, and this is our answer right here. Oopsie, this is what we have right here. All right, so now what about the graph? Well, here's what my graph looks like. So let's compare that with yours. And if you trace it, what do you see? Well, remember here, I want to be below 8,000. So I'm going to look to see when the y is less than 8,000. I see the y is less than 8,000 after 22 years. So what's our answer going to be? It will take about 22 years for the population to reach 8,000. Okay, ladies and gentlemen, that's pretty much going to wrap up the new material for today. Your assignment for next class period, and we're going to do this in class, so don't get started on it yet, is going to be in sections 7-1, 1 through 6, 12 through 14, 16, 18, 42, 44, and 48. All right, well, that wraps it up, and I guess it's time for me to sign off. Have a good day.